Here we have something really beautiful. X to the power of e equals e to the power of x. At first glance, it might seem like there could be many solutions, or maybe even none. But as we'll see, this innocent-looking equation is actually hiding some beautiful structure. The first thing we need to ask ourselves is what values can x actually take? It might be tempting to just dive in, but there are some important constraints we need to consider. Let's start with the simplest case. What happens when x equals 0? Well, 0 to the power of e is just 0, but e to the power of 0 is 1. That gives us 0 equals 1, which is clearly false, so x can't be 0. What about negative values? Here things get a bit more subtle. If x is negative, then e to the x is still perfectly well-defined and positive, but x to the power of e becomes problematic. We're trying to raise a negative number to an irrational power, which isn't a real number. Since one side is real and the other isn't, there's no way they can be equal. So we can restrict our attention to positive values of x. This makes sense because both sides of our equation will be positive real numbers. Before we dive into the algebra, let me build some intuition by testing a few specific values. Sometimes the best way to understand a problem is to just try some numbers and see what happens. Look at what's happening here. When x equals 1, e to the x is bigger. Same thing when x equals 2. But right at x equals e, they're perfectly equal. Then when x equals 4, e to the x is bigger again. This suggests that x equals e might be the only solution, and it happens right at the sweet spot where these functions cross. Alright, intuition is great, but let's be more rigorous. The key insight is to transform this equation into something we can actually work with algebraically. Starting with our equation, since we know x is positive, both sides are positive, which means we can take the natural logarithm of both sides. This is a classic move when dealing with exponential equations. Taking the natural log of both sides. Now I can use the logarithm power rule to bring those exponents down front. Remember that the natural log of e is just 1. So the right side becomes just x. Much cleaner. Now here's the key move. I want to divide both sides by x. Since we know x is positive, this won't cause any problems. Dividing by x. The right side becomes 1. And dividing both sides by e gives us this beautiful form. We need to find where the function natural log of x over x equals the constant 1 over e. This reformulation is going to make everything crystal clear. Now let me show you why this reformulation is so powerful. We can visualize exactly what's happening. I'll plot both sides of our equation. The blue curve is our function natural log of x over x, and the green line is the constant 1 over e. Look at this! The horizontal line appears to be tangent to the curve right at its peak. If that's true, then there's exactly one solution. But to know for sure, we need to use calculus to find where this function reaches its maximum. Let's be rigorous about this. I want to find the maximum of the function f of x equals natural log of x over x. So here's our function. To find the maximum, I need to take the derivative and set it equal to 0. Since this is a quotient, I'll use the quotient rule. Quick reminder about the quotient rule. When you have a function that's one thing divided by another thing, the derivative follows this pattern. Derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. It's like the product rule, but with that crucial minus sign and the extra bottom squared in the denominator. Applying the quotient rule to our function. The derivative of natural log of x is 1 over x, and the derivative of x is just 1. Simplifying gives us this clean expression for the derivative. Now, to find the critical points, I'll set this derivative equal to 0. So I need to solve this equation. A fraction equals 0 only when the numerator equals 0. Rearranging this equation. To solve for x, I'll exponentiate both sides. So the critical point occurs at x equals e. Beautiful. Now let's see what value the function takes at this critical point. Plugging e into our function. The maximum value is exactly 1 over e. And there's our proof. The function natural log of x over x reaches its maximum value of 1 over e at exactly one point where x equals e. Since the horizontal line is at this exact height, it touches the curve at exactly one point. This confirms that x equals e is the unique solution to our original equation. But wait, there's an even more elegant way to see this. Let me show you a perspective that reveals some beautiful symmetry. Going back to our original equation, what if I raise both sides to the power of 1 over e times x? This might look messy, but watch what happens to the exponents. Using the power rule to multiply exponents. Look at that symmetry. X to the 1 over x equals e to the 1 over e. This gives us another way to think about the problem. We're looking for where the function g of x equals x to the 1 over x has the same value as g of e. It turns out this happens exactly when g reaches its maximum, which occurs when the natural log of x over x is maximized. Full circle. So far, we've only considered real solutions, but what if we venture into the complex numbers? Then things get really interesting, and we need a more advanced tool called the Lambert W function. First, let's understand what the Lambert W function actually is. It's defined as the function that satisfies this elegant equation. W of z times e to the w of z equals z. In other words, it's the inverse of the function f of w equals w times e to the w. This base function, w times e to the w, appears everywhere in mathematics factorial. It shows up in population dynamics, circuit analysis, quantum mechanics, and even in the analysis of algorithms. The Lambert W function gives us a way to undo this operation. Now, here's the brilliant connection factorial. Let's manipulate our original equation. From x to the e equals e to the x, we get e times natural log of x equals x. Dividing by e, we get natural log of x times e to the natural log of x equals x over e. This is exactly in the form where we can apply the Lambert W function. So natural log of x equals w of x over e. But we want to solve for x, not natural log of x. Taking the exponential of both sides gives us x equals e to the w of x over e. But wait, this still has x on both sides. This is where the magic of the Lambert W function really shines. We need to be more clever about our substitution. Let's try a substitution. Let y equal natural log of x. Then our equation becomes y times e to the y equals e to the y minus 1. We're getting closer to the Lambert W form, but we need to massage this a bit more. If we multiply both sides by -1 and rearrange, we get negative y times e to the negative y equals -1 over e. Perfect. This is exactly the form we need for the Lambert W function. Therefore, negative y equals w of -1 over e, which means y equals negative w of -1 over e. Since x equals e to the y, we get our beautiful solution, x equals e to the negative w of -1 over e. Now here's where things get truly fascinating. The Lambert W function has infinitely many branches in the complex plane, denoted 1 w subscript k, for integer values of k. This reflects the fact that complex logarithms are multivalued. There are infinitely many ways to undo the exponential function in the complex numbers. Let's verify the principal branch. W subscript 0. We have w subscript 0 of -1 over e equals -1. Let's check. -1 times e to the -1 equals -1 over e. Perfect. So the principal branch gives us x equals e to the negative of negative 1, which is e to the 1, which is just e. There's our familiar real solution factorial. But here's something interesting. The negative 1 branch also gives w subscript. Negative 1 of negative 1 over e equals negative 1. Wait, that gives us the same solution x equals e, again factorial. This happens because negative 1 over e is exactly at the branch point where w subscript 0 and w subscript negative 1 meet. For all other values of k, the branches dw subscript k of negative 1 over e give us complex numbers. These correspond to the infinitely many complex solutions to our original equation. Each one represents a different way that x to the e can equal e to the x in the complex plane. For instance, w subscript 1 of negative 1 over e is approximately negative 1 plus 2 pi I. This gives us a complex solution x approximately equal to e to the negative of this complex number. The beauty is that this complex number, when raised to the power e, actually equals e raised to the power of this same complex number. So there you have it. What started as a simple equation revealed layers of beautiful mathematics, from basic algebra to calculus to complex analysis. If you enjoyed exploring this problem with me, please consider liking this video and subscribing for more mathematical adventures. Until next time.